Okay, I just hit the record button. I'm glad I remembered. Before I erase the board, make sure that I take a picture. I just kept the camera on the side. Okay, I'm going to stand up. Let's get started. I think you can see me. So we're talking about aromatic compounds, and we talked a little bit about the history of aromatic compounds. I mentioned that the first compound that turned out to be aromatic because it created a brand new category of compounds. It's an unsaturated compound, but it's not just like any alkene. It's more than an alkene. The first molecule that turned out to be aromatic, and that was first identified by chemists many years ago, had the empirical formula C6H6. Our empirical formula would have been C1H1, and the molecular formula was C6H6. And people had a lot of hard time figuring out what the molecule looked like, and we discussed it, and eventually the structure was found to be cyclic. Okay, so it's not this. This was one of the crazy recommended structures. This was not that, and it showed some weird chemistry, because when it was reacted with bromine, unlike other alkenes or alkynes, this guy did not react. This guy did not react, but then it reacted when the chemists during that time added some iron trichloride, ferric chloride, along with bromine. Then it was beginning to react with the molecules. Fe Br3. So it turned out that the molecule was this. This is a very brief review. Okay. Then when you reacted it with one more molecule of bromine and one more molecule of iron tribromide, it again reacted. C6H4, you realize that each time you lose a hydrogen and you add a bromine. So one hydrogen is replaced with a bromine. The second hydrogen is replaced with a bromine. And then when you react third time, the third hydrogen is replaced with a bromine. Okay. Okay. So this reaction happens 3 times, and it turned out that this molecule is much more bizarre and weird and strange structure-wise than anything else that the chemists had seen until that time. And you know, the hair pulling probably happened for more than a decade, probably more than 2 decades, and eventually Kekulé cracked the structure, and it turned out that this was the molecule. Kekulé was the first chemist who proposed that benzene, this particular molecule C6H6, is cyclic. And this is what the molecule looks like. Okay. This is benzene, and its formula is C6H6. Is the board causing too much glare, or we are good? Board is okay? Anybody has anything? You can make your comment heard by unmuting yourself and speaking out.
It looks good.
It's good? Okay, nothing in the chat. So how many of you are there right now? 32. The attendance is diminishing slowly. Okay. All right, so this is the molecule. So what's so special about it? What's so special about it is that when you have a structure like benzene, a cyclic structure, and you have alternate double bonds and no gap in between, double bond, single bond, double bond, single bond, double bond, single bond. When you have an arrangement like this, and when these molecules, when these specific molecules follow a certain rules, not just being cyclic and having alternate double bonds, there are few additional rules. Excuse me. When they follow the rules, when they meet the requirements, these molecules are more stable than what the chemists would have expected. So you would expect that as you go from single bond to double bond, the molecular energy, their unhappiness, their instability will increase energy-wise. Energy goes up this way, right? When you have no double bonds, you are happy. It's very stable down here. You add a double bond, the energy goes up a little bit. You add a second double bond, energy goes up more. Add a third double bond, energy goes up this much. And that's very standard. That's understandable. That follows the rules until new rules come about. For this molecule, benzene, and other similar aromatic molecules, it turns out that when you have the cyclic structure, alternate double bonds, and few other rules, they're not as unstable as you would expect. And that stability is called aromatic stability. I'm going to break it down and explain, okay? So imagine this is my boundary. Imagine the molecule with 6 carbons. So we are dealing with compounds that have 6 carbons. I'm going to keep that number to 6. Okay. So the happiest molecule, hydrocarbon, you can think about with 6 carbons and bunch of hydrogens would be what? Anybody wants to say something? You can either write it on the chat. You can name it. You can name the molecule. You know the molecule that has 6 carbons and whole bunch of hydrogens, most saturated compound. What compound is that? Anybody wants to pop it in the chat group? It starts with an H. What compound is that? Write something up or say something.
Hydrogenated.
Hydrogenated. It cannot take any more hydrogens. 6 carbons and bunch of hydrogens. It doesn't have to be cyclic. What compound are we talking about?
Hexane.
Hexane, very good. So hexane looks like this. And let's say that if this is the energy, if energy goes up from down to up, and lower we draw the molecule, that means it's more stable. If we draw it a little bit higher, it's more unstable. You know, our old convention. It's not that difficult, right? You guys can see the red vertical line with the arrow up? Yes?
Yes.
Okay, good. So this is hexane. Remember, don't forget, I mean, I know that the spring break might have done more damage than good. I hope you have gotten some time to relax and build up your charge up your battery, but just make sure you're on top of the knowledge that we have acquired so far in this semester. It's been a crazy time. So this is hexane, right? This molecule that we're dealing with is not cyclic. It's not acyclic, it's cyclic. So let's start working on cyclic molecules. So if this is hexane, and if its energy is down here, if we draw cyclohexane, so this is cyclohexane. This is cyclohexane. We have dealt with cyclohexane quite a bit in the past, right? Chair form, chair can flip, just reminding you, chair can flip, chair, when the chair flips, it goes through the boat. Remember, if the chair is like this, if this is the backrest, this is where you sit, and if this is your footrest, you can push the footrest up, right? When you push the footrest up, it's kind of like a boat. That's really bad. When you push the upper end of the boat, the right side, which was the normal sit backrest for the chair, when you push it down, then it goes to the other chair where the backrest is on your left and footrest is on your right, unlike the way it started. It started out the other way. So chair flips from chair to boat to chair. Boat is bad because boat has eclipse conformations along these two carbons, and it also has the flagpole interaction. That's not good, okay? Because of those two reasons, boat is bad. Chair, every two adjacent carbons are staggered. They're not eclipse. So chair is good. That's this, okay? I don't want to talk about cyclohexanes right now. So this is cyclohexane. As I have drawn cyclohexane slightly above hexane, that means you're decreasing its entropy. Entropy means freeness. Like if my hands and my legs are, I can flip them around, then my randomness is more. Okay, if I put my hands, if I'm on handcuffs, let's say I get arrested for DUI and the cops put handcuffs on me, that means my entropy is less, my randomness is less, my order is more. Okay, I don't have to teach you order and chaos and randomness and entropy. It's not part of the exam, it's not part of your learning, but I think it's good to understand that. So from hexane, when we go to cyclohexane, entropy goes down and its internal energy goes up, okay? So that's why it's drawn slightly higher up. Now what I'm going to do is I'm going to start throwing in double bonds in it. So when we go from cyclohexane to cyclohexene, this is called cyclohexene. Okay, the energy gap between cyclohexene and cyclohexane, let's say it's delta E. Okay, whatever the energy gap is, from here to here, that gap, let's say it's delta E. Whatever delta E means, delta means small. It's a change. So it's going from cyclohexane energy to cyclohexene energy, and the difference between them happens to be delta E. Okay, let's call it delta E1 for the first double bond. Now let's do something else. Now let's put a second double bond in the molecule. So now we have cyclohexane with two adjacent double bonds. And you would expect the energy gap to be, you would expect this number to be 2 times of that, okay? So it should be, let me clean up this place so that you can see, it should be 2 times delta E1. You know what? Let's lose the 1. We don't need that. It's just making things unnecessarily complicated. The delta E is going from here to here. Cyclohexane to cyclohexene is delta E. Cyclohexene to cyclohexadiene should be delta E. It's not 2. Sorry, my bad. I'm getting a little, I think this is, let's blame it on the spring break. We shouldn't have had the spring break. I'm forgetting my basic chemistry and mathematics. So if this gap, if by putting one double bond, you make the molecule unstable by delta E, by sticking a second double bond, you make this guy more unstable by another delta E. Are we good? If we're not good, then say something or write something on the chat. No double bond cyclic molecule, you have your energy is whatever, let's say here. You stick one double bond, it goes up, the energy goes up. You're disturbing the system, you're increasing the internal energy, and the energy goes up by whatever delta E. You stick a second double bond, the energy goes up by 2 delta E from down here, or from here another delta E, right? So it's not that difficult. Now what you do is you stick a third double bond. And the gap between 2 double bonded system and the 3 double bonded system, now you can see that it's beginning to look like benzene, right? We won't call it benzene. We're going to pretend that it's not benzene. It's a 3 double bonded cyclohexane system. Let's pretend that we don't know what's going on with benzene. Okay, so if we put a third double bond, your expectation, the chemist's expectation at the time, long time ago, many more than a century ago, was that the gap between here and here should also be delta E. So this gap you expect to be delta E. What do you guys think was the real life scenario? Was the real gap delta E, or was the real gap less than delta E? What do you guys think? Was this molecule as unstable as predicted, or it was less unstable than what the prediction was? What's your gut feeling? What do you think? Less. I think it was less. Yes, you guys are right. I'm not going to dramatize our lectures anymore too much. So the real number, this was not delta E. Real number was less than delta E. Okay, and this was a big deal. And this is why, because that real number was less than delta E, that's why we have a whole chapter, sometimes more than one chapter, is dedicated to aromatic compounds. When this happens, when the molecules, the cyclic molecules, follow certain rules and guidelines, then their energy is less than expected. They're not as bad. They're not as unstable as just any double bonded species is, okay? They are not as eager to react with bromine. You cannot hydrogenate them. You cannot react it with hydrogen gas and a catalyst and expect all the double bonds to disappear and make cyclohexane from benzene. That doesn't happen. You cannot just throw bromine and pretend that the bromine is going to stick and the red color of bromine will go away. That doesn't happen. Because the molecule is happy, they don't care about these normal reactions that would be more prevalent with just a single double bond or a triple bond. They are not just a single double bond or a group of double bonds. They're not like that. There is something weird, something funny, something stabilizing happening with this arrangement. Okay, so it's much less than delta E, and that gap, I'm going to write it down in this. The special energy stabilization is aromatic. I'm all over. Is aromatic stability. So when the molecule is cyclic and blah, 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 it follows certain rules, bunch of rules, then what happens is the molecule is much more stable than expected. It's supposed to be here energy-wise, but in reality, it's down here. So that gap, expectation versus real life scenario, that gap is called aromatic stability. And we say these molecules are aromatic because they have an aroma, and they're, for whatever strange reason, these guys are super stable. They don't like to react with bromine. They don't like to undergo hydrogenation reaction with hydrogen gas and catalyst, unlike anything else in the whole world. These guys are weird. And that's why we have a chapter or bunch of chapters totally dedicated for this compound, to discuss this compound, because they're totally different than anything else scientists had ever seen in their life. So I'm going to stand on the side. You guys take a look. I'm going to take a picture. And so this is our introduction to aromatic chemistry. Let me take a snap. I'll send it to you guys, and I'll also add the video. Okay. Any questions so far? Let me see your chat. Doesn't look like you guys have any questions yet. You can also unmute yourself and talk. It's totally fine with me. Okay. All right. So let me erase part of the situation here. Okay. Let me erase as much as I can. I need to clean my board a little bit more carefully. Let's use all the space we have. So, aromatic compounds. What's so special about those aromatic compounds? What are the rules for a compound to be aromatic? Okay, and we know one example. We know that this guy is aromatic. Okay, that's C6H6. C6H6, how many pi bonds does it have? How many pi bonds does it have? You can speak or you can write. 3. Okay, I'm not going to ask you how many sigma bonds do you have. Bunch of sigma bonds. Let me ask you a couple of questions. I'm very tempted. Can you predict what I'm going to ask with the green arrow? You can speak up, unmute and say something.
The hybridization.
I'm going to ask. What am I going to ask?
The hybridization.
Yeah, hybridization. What's the hybridization? SP or SP2 or SP3?
SP2.
Very good. What's the bond angle here? The red arrow. What's the bond angle? 90, 120, or 109.5?
120.
My favorite question. What's my favorite question about benzene? I'm going to give you a hint. I don't think I have my frisbees here. I'm trying to send you a message. What am I going to ask about benzene?
Is it planar?
Is it planar? What's the shape of benzene? What's the shape of benzene? You can write or you can say something. Yeah, 120 is the right answer. Thank you. Thank you all. The entire molecule is planar. Okay? Perfectly planar. It's flat like nobody's business. Okay? The 6 carbons and the 6 hydrogens, they're perfect planar. Okay? And that's why when you have graphite, what happens with graphite? You have multiple aromatic systems like carbon, carbon, carbon. They're all hexagonal. Okay, they're really weird. Well, I'm getting distracted, but I'm going to try not to get too distracted. You can have polyaromatic systems which are kind of like that, and when you have those sheets, one sheet kind of floating on top of the other sheet, then you get that graphite-ish feeling, okay? Like the layers are kind of sliding one on top of the other. I'm going to try not to get distracted. It's not time for distraction right now, even though I'm looking for something different that's going to cut this monotony of life, staying at home. So this is planar. Okay, good. So stay on top of hybridization, stay on top of bond angles, stay on top of the structural aspects of different molecules, okay? You're doing good. Hopefully everybody is on board. All right, so we know that, let's do a little more chit chat about aromatic compounds. That this is hexane, it's not aromatic. And if it is not aromatic, I'm going to put like a cross, okay? Not aromatic. And for being aromatic, I'm going to put like a green check mark. That's aromatic. So when you have this guy, how'd you name it? Let's practice our old knowledge. How'd you name this guy? Say something. Say, unmute and speak up.
1-hexene.
Sorry?
1-hexene.
1-hexene. Sounds good. So this guy is 1-hexene. Okay? Do you think it's aromatic? Doesn't smell like an aromatic compound. I really do not know how it smells, but then it's not aromatic. I'm just going to say no. Okay? If we put 2 double bonds, let's not name the molecule because it's beyond our area of expertise. So it's whatever it is, not aromatic. If we put 3 double bonds, 1, 2, and 3, excuse me, it's not aromatic. We know that when we have cyclohexane, it's not aromatic. Okay? We know that when you have cyclohexane with 1 double bond, it's not aromatic. We know that when we have cyclohexane with 2 double bonds, even then it's not aromatic. But when you have cyclohexane with 3 double bonds, it's aromatic. It's aromatic. This pen really, I'm going to drop this pen. Okay, so there is some of the rules might be slowly popping up in your mind that, you know, these are the rules that must be followed for a compound to be aromatic. So let's write down the aromatic rules down here. Rules of aromaticity. Number 1. What's the first rule? This is not aromatic, that's not aromatic, that's not aromatic, that's not aromatic. This guy is aromatic. What's the difference between their structures?
It's in a chair confirmation.
You're making things more complicated. One is not something. The difference between my hands now and now. I'm not in chair confirmation, but what am I trying
Not
to do?
cyclic.
It's sorry?
It's not cyclic.
It's not cyclic. So it has to be cyclic, right? Rule number 1 is the molecule must be cyclic. Okay, rule number 1, if you have an acyclic compound, not cyclic, forget about it. There is no way it can be aromatic. No way. Rule number 1, must be cyclic. Rule number 2, this is not aromatic, but take a look at the board and see if you can formulate rule number 2. What must be present in the cyclic molecule? Cyclohexane doesn't work. Cyclohexene doesn't work. Cyclohexadiene with 2 double bonds doesn't work. 3 double bonds work. So how do you put it in words? How do you make a rule after watching something happen and repeat itself over and over and over and over? And you say, oh, wow. So if there are like 7 birds, they're going to flock in this shape. They're going to fly in this shape with 1 in the front and 3 in the back and then 2 and then 2. I'm just making up some story, okay? So when you see that happen like 100 times, then you say, well, so there are 7 birds will always fly in the shape of this, like an airplane, okay? With a little wing and a little cockpit and a little tail. So how do you come up with rule number 2 based on the double bonds? Think, no answer is a bad answer. Make an effort, try. Alternating double bonds from Sarah. Excellent. Resonance structure, yes. You're thinking too far ahead. Yeah. So alternating, perfect. Alternating double bonds. Excellent. That's perfect. This word is very important, alternating double bonds. Okay. Now I'm not going to ask any questions. I'm going to just kind of fill in. So under this alternating double bonds, one thing that's that kind of comes as a sub rule of this rule, but I'm going to make it a brand new rule. Okay. Another rule is, I call it, so get used to this nomenclature that was invented by me. Okay. I call it a sigma wall. What I mean, I'll explain what I mean by that. No sigma wall. Do you know what I'm talking about? This end, let's say this end. Okay, let's move the cross. Okay, this location. What do you have here? You have a carbon. It's attached to another carbon. It's attached to another carbon. It's attached to one hydrogen and one hydrogen. What are all the 4 bonds made out of? What kind of bonds are all those 4 bonds around that carbon? They're all sigma. That's sigma, that's sigma, that's sigma, and that's sigma. So you don't want that to be the situation in one of the corners of your cyclic molecule that you're trying to figure out whether it's aromatic or not. You cannot have one corner which is made out of nothing but sigma bonds. That's bad. That's not going to work. So that's what I call sigma wall. This is like you need to flow the electrons. What a couple of you wrote, the resonance structure, you are absolutely right on, but I don't want to talk about it now. I'm going to wait a little bit longer. Okay. So this is sigma wall. Sigma wall means you are dead meat. You cannot flow your electrons through the sigma bond. You need a pi bond or you need something else. Okay. Sigma wall is absolutely prohibited, forbidden for compound to be aromatic. Okay. So this is a bad idea. Let me just move this writing a little bit down here. So this is sigma wall. Sigma wall means all sigma, no pi bond. This is not a sigma wall. This is not a sigma wall. This is not a sigma wall. This is good. This is good. This is all sigma. This is all sigma wall. They are all sigma walls because you don't have any pi bond. Whenever you have a pi bond, it's good. Pi bond is not sigma wall. Okay. This is good. This is good. This is good. 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 Not good. Not good. Not good. Not good. These are all sigma walls. This is not. This is fine. This is fine. So whenever you have a double bond, the 2 ends of the double bond is fine. But whenever you don't have a double bond, you have nothing but sigma, or you can think about it like an sp3 carbon. When you have an sp3 carbon, that's bad news. Okay, sp3 carbon is bad news. Maybe, you know what? I'm going to just add it here. sp3 carbon is, I can't erase using my old bad habits, is bad. Okay, you get that? Okay, we have lot more to discuss. I'm going to open the door a little bit because it's getting kind of stuffy. I'm going to also turn on my fan. Okay, so sigma wall is bad, but so this is kind of like an extension of the double bond scenario. Alternating double bonds is good. Sigma wall is bad. They're kind of like complementary, right? You might say, Dr. Maitra, but didn't we already say that alternating double bonds are necessary? That means no sigma wall, right? Yeah, but it's a little sketchy scenario. You will see what I'm talking about when I write the next rule. The next rule is sigma wall is bad. Double bonds are needed, alternating double bonds, but if you don't have either of them, you might have a completely different scenario, which is this. You may have a carbocation or a carbanon or an atom with 1 or 2 lone pairs. That's okay. Carbocation cation, or I'm going to use different colors, carb anion, or a heteroatom. Heteroatom means not carbon, not hydrogen, something like nitrogen or oxygen or phosphorus or sulfur, something other than carbon, okay? Carbocation, carbanion, or heteroatom with one or two lone pairs. Okay, maybe okay, maybe okay. So the bottom line is you may not have a double bond or a sigma wall, but you may have a scenario with a positive charge. That may be fine. Or you may have a scenario when you have a carbanion. That may be fine. Or you may have an oxygen with two lone pairs. That may be fine. So this may be okay. This may be okay. This scenario may be okay. Having a carbocation may be okay. We do not know. There is one last rule that you need to take care of. Okay, so this may be okay. Having a lone pair, having a negative charge may be okay. Having a positive charge may be okay. But just sigma wall, carbon with bunch of sigma bonds, that's not okay. Okay, and you generally have to have alternating double bonds. Okay, I'm going to write the last rule and then I'm going to take a little pause and try to catch a break. Okay, the last rule. Total number of, I'm going to introduce a new word, labile. The book says pi electrons. I like to use the word labile electrons. I'll explain why. Total number of labile electrons should be able to be written as a formula. I'll explain what that formula is because this formula causes a lot of trouble. The formula, there is a little bit of math, just a little bit of math. The formula doesn't fly very well with our students, with you guys. So you will have to really pay attention, and that's what I want to accomplish today. And then I'm going to go over some examples of different types of aromatic compounds. Okay. Total number of labile electrons, I'll explain what I mean by labile electrons, must be written as 4 multiplied by n, small n as in Nancy, plus 2. So the total number of labile electrons must be written as a formula 4n plus 2. I'll explain. What is n? N is any integer, any number, not fraction. Whole number. Examples: 0, 1, 2, 3, 4, 20,000, 5 million, whatever it is. Any number is fine, but it cannot be half, it cannot be 3/7, it cannot be 3/4, it cannot be any funny number like that. No fraction, it has to be a whole number. I know that you guys are still pretty confused. You're probably wondering, like, I don't know what he's talking about. Just hold off on that. So just for the time being, just know that the total number of pi electrons or labile electrons must be, let's say the total number of electrons is 55 or 54. Can you write 54 as 4n plus 2 using a value of n? If you can, then the molecule may be aromatic. If you cannot, then the molecule probably is not aromatic. Okay, I'm talking like somebody in White House, probably, maybe, could be, you should, could, maybe it will help you. Okay, labile electrons. What is labile electron? Labile electrons are pi electrons, pi bond electron. Pi electrons plus, if you have a negative charge, then those two are also labile electrons. So you count those, negative charge. If you have an oxygen with a lone pair, you count. So pi electrons, negative charge, those electrons plus lone pair. Those electrons constitute the definition of labile electrons. So what we're going to do is right now, excuse me, is take a little break. I'll let you guys look at the board and kind of stare at it. In the meantime, I'm going to take a picture.
Dr. Maitra?
Yeah.
I don't know if it's just me, but I can't see the bottom portion. Like after lone pair.
Oh, after lone pair, okay.
I really can't see the bottom.
Yeah. Okay, I got it. Thank you. I'll rewrite that part. So what I have written here is n equal to 0, 1, 2, 3, 4, 5, 6, 20,000, 50,000, something like that. That's all I have written down here. You're not missing much. And I'm going to take a picture and I'm going to upload it anyway. So you will be able to see it on Canvas eventually. I'm going to block you for a second, whatever it takes me to take the snap. Okay, got it. So what I want you to do now is to kind of get a feel for what might be aromatic, what might not be aromatic. We will work through the rules. We will walk through the last rule number of times so that you guys get it. You guys understand. Hop cars. They're probably keeping an eye on me. Straight chain acyclic is not good. So the first rule is the molecule must be aromatic. Sorry, the molecule must be cyclic to be aromatic. That's rule number one. Molecule must have alternating double bonds. Generally speaking, there are some exceptions. So take this with a pinch of salt. Alternating double bonds is great, like this guy, alternating double bond, this is fantastic. You cannot have a sigma wall, that's really a bad idea. If you do not have a double bond, but you have a carbocation, or you have a carbanion, or you have a lone pair or two lone pairs, it might work. It might work. What's that might doing here? That little word that's making things iffy? Well, you still have to count all the electrons that can participate in resonance. We're going to also learn resonance at this time, probably today and partly on Wednesday. Okay, so resonance means the electrons are spinning around like crazy. Okay, so labile electron, labile means mobile, kind of like mobile. Like I'm being very labile or stationary. The opposite antonym of labile will probably be stationary or stuck or stagnant. Okay, labile means something that's movable. Okay, the sigma bond electrons, these electrons, these electrons, these electrons, these electrons, these electrons, they are not labile. The pi bond electrons are labile because they can spin around, they can move around, they can delocalize themselves. We're going to talk about those terms shortly. Must be cyclic, must have alternating double bonds. Sigma wall is bad idea for it to be aromatic. Carbocation, maybe okay, in between double bonds. carbanion in between double bonds. You don't have a sigma wall, but you have a carbanion. It may be okay. Then what you do is you count all the movable electrons. How do you count them? Count the pi bonds, find out how many electrons in each pi bond, add them up. If you have a carbanion, you add 2 for that carbanion. If you have a carbocation, there is nothing. You add 0. If you have lone pair, if you have only one lone pair, you add 2. If you have 2 lone pairs, you add half of them. If oxygen has 2 lone pairs. So you might wonder, so what shall I do? Shall I add 4 or shall I add 2? You add only 2 because at one time, only 2 electrons can mess around with the delocalization, that spinning business, okay? So you add them up and see what the number is. Let's say the number is 24. Now the next question is, can you write 24 as a formula? The formula is 4n plus 2 with a value of n, which is not a fraction. We will work on that. So this is what we have learned so far. So I'm going to erase the board after you guys have kind of glanced at it for 15 seconds. Take a look. If you have any questions, you can always unmute yourself and throw a question in the online world. Read the rules, kind of try to remember them, because it's going to be very important. What we're discussing today is very important. There is going to be a quiz on Wednesday for you guys and Thursday for the other class. A shorter time period quiz because I gave you guys way too much time, the first one. And it's going to be multiple choice, maybe 5 to 10 questions. And what we're learning today is important. Let me just take a look at the chat. Nobody's write anything here. Okay. Are we good? Are we doing good? Following everything reasonably well? Okay, now let's do some experiments. We learned the trick of the trade. Now it's time for us to be stepping out in the real world and apply our knowledge. Okay, what I'm going to do is I'm going to rewrite the rules in maybe a little cleaner. Let's rewrite the rules. I'm going to erase the top. All right, how are we doing with time? Okay, we have 20 more minutes. Okay, rules, aromatic rules. Aromatic rules. I'm just going to shorthand it, so I'm not going to write the whole story. Number 1, cyclic. Number 2, alternating double bonds. Number 3, no sigma wall. Number 4, carbocation, carb, anion, or lone pair. Okay, and the last rule, total labile number of labile electrons should be written as 4n plus 2, where n is a whole integer. Examples 0, 1, 2, 3, 4, 12, 500, 10,000, whatever it is. Okay? These are the arithmetic rules. We're going to practice. These are the arithmetic rules. Take a look. Kind of mentally just murmur through the rules. Cyclic, alternating double bonds, no sigma wall, carbocation, carbanion, lone pair may be okay. Total number of electrons must be written as 4n plus 2, and then it's aromatic. If you have any questions, ask me right now. $33. You guys are disappearing.
Dr. Maitra?
Yeah.
Yeah, can you explain one more time about why sigma wall is not good?
Well, let's do some examples, then we will understand. It has to do with the question is, when in asked why sigma wall is not good. Well, I haven't explained why these rules make a molecule aromatic. The bottom line is what some of you had already anticipated, that resonance has to happen. Resonance means, think about these cyclic systems like the periphery of your house with bunch of posts. I'm sure one of you in this Zoom classroom has heard it before. And there are posts, and think about them like little monkeys sitting on top of the post around your house. And the monkeys are jumping from one post to the other. And the monkey who was sitting in the post in the front is pushed to jump into the other post. So they're basically doing their monkey business by running around the house, the periphery of the house, on top of the posts. So each post is like a carbon, and the monkeys are like pi bonds, pi electrons, or labile electrons. So they're spinning around. So when you have a sigma wall, nothing but sigma bonds, the monkey cannot jump. It's kind of like a wall. It's really like a wall. So they cannot spin around the house. In order for the molecule to be aromatic, to be stable, the monkeys or the electrons must be running around that peripheral path, okay, along that hexagonal path or whatever the shape of the molecule is. It doesn't have to be a hexagon. We will see that pretty soon. So that's why it's a bad idea to have a sigma wall, okay? Let's do some examples. Okay, let's take the simple molecule. I'm going to draw out everything, and this was our first example of an aromatic compound. So don't say aromatic or not aromatic. Let's go through the rules. Rule number 1, is it cyclic? Can someone say yes or no?
Yes.
Yes. Do we have alternating double bonds?
Yes.
Yes. So we have alternating double bonds. So we don't have to worry about sigma wall, carbocation, carbanion, blah, blah, blah. Okay? When you have alternating double bonds, you're done. You don't have to worry about, where is the carbocation? You're wasting your time, because if the rule for alternating double bonds is met, you don't have to worry about pi bonds being compensated by other things like a carbocation, carbanion, lone pairs. Okay, you don't have to worry. So skip these rules. Which rule you cannot skip? The last rule. Okay, how many labile electrons does benzene have? Tell me, how many pi bonds do they have? We already answered 3. So that's a pi bond. Let's color them. That's a pi bond. This is a pi bond. And this is a pi bond. How many electrons does each pi bond can hold?
2.
2. There are 2 electrons here. there are 2 electrons here, and there are 2 electrons here. So altogether, how many labile electrons does benzene have? Let me hear it because I'm not looking at the screen. How many labile electrons does benzene have?
6.
6.
Number of labile electrons is 6. Now comes the complicated mathematical part. Okay, it's not mathematics. Can you write 6 as 4n plus 2? One of my students, I don't remember when and what circumstances, which class it was. I think it's a good idea that we solve for n. I think this came from one of your classmates in the past, not your current classmate, but I'm generalizing the definition of classmate. So let's solve this equation. How do you solve the equation? Don't tell me you cannot do it. You can do it. So keep 4n on the right side, move 2 to the other side. 6 minus 2. You should know that when you move things around, when you put the dining table from the right to the left, it becomes a negative dining table. 6 minus 2, right? 6 minus 2 is what? 4 equal to 4n. Then what's the value of n? 4 over 4 equal to 1. So n turned out to be a whole integer, which is 1. So when n equal to 1, the total number of pi electrons or labile electrons, is 6. That's a good number. Remember that. When you have 6 labile electrons in a cyclic system with alternating double bonds, the molecule is aromatic. So this is aromatic. I'm going to take a 15-second break and make sure that you follow it. You better follow it, because if you don't follow it, the future holds misery and tears for you. Tears and jeers and misery, on top of getting your boredom fixed. I don't know how am I going to fix my boredom. A lot of people are buying pets. A lot of people are giving up their pets. Maybe I'll catch a squirrel. Force him to be my pet. I'm not going to do that, so don't call the cops. Are we good here? Say something. I'm not going to look at the chat. If you have any questions.
We're good.
Okay, very good. Thank you. Now let's do this. Let's do this molecule. Can you tell me if this is aromatic? Let's unmute yourself and say the rules. Rule number 1, is it cyclic? Say yes or no.
No.
Yes.
It is cyclic. It looks like a box, but it's cyclic. Cyclic means it's not open. It's not dangling at the 2 open ends. It's somehow tied up. How big the cycle, triangle, hexagon, pentagon, octagon, decagon, whatever it is, that's a different story. But it is cyclic. It's not, it doesn't have any loose end. Cyclic. Okay. So rule number 1, check. Rule number 2, does it have alternating double bonds? Just say yes or no. Don't jump.
Yes.
Rule number 2 is good. Should we worry about sigma bond and carbocation, carbanion? No, because we already have alternating double bonds. Is this molecule aromatic or not? How many pi electrons does this molecule have? 2 here and 2 here. So total number of labile electrons is what? 4. The question is, can you write 4 as a formula, 4n plus 2, with the value of n being a whole integer? So one way you can solve it is by figuring out what the value of n is. 4n equal to 4 minus 2 equal to 2. That means n equal to 2 by 4 is half. So in order for 4 to be written as 4n plus 2, the value of n that you need to plug in is half. Does it make that molecule aromatic, or is this not aromatic? What's your answer?
Not aromatic.
Not aromatic. Fractions don't work. Not aromatic. Got it? Are you guys following? Aromatic or not aromatic?
Yes.
Yes.
Okay. Let's do one more example. So this was these were the two examples. This is molecule 1, molecule 2. Let's do another molecule. Let's do this molecule. I'm going to draw 3 molecules. So let's say this is molecule number 1. This is molecule number 2. This is molecule number 3. This is molecule number 4. This is molecule number 5. And this is molecule number 6. Okay. We have 4 more compounds written, and I want you to use the rules and figure out, this is exactly how some of the questions are going to be asked in front of you when you take the next quiz or next exam. Okay, I might say, is this out of these 7 molecules or 6 molecules, which compounds are aromatic, which compounds are not aromatic, and justify why or why not. Tell me why it is aromatic, tell me why it is not aromatic. You just write maybe 1 or 2 words or 5 words or a couple of sentences, then you get all your points. Now, molecule number 3. How do you justify? Can somebody think about it in your head, unmute yourself, and speak loudly and crisp with a crisp voice, which is legible? Explain what do you think about the whole scenario? Molecule number 3. Is this aromatic?
I don't think it's aromatic.
What's the problem?
It has 2 or 4 liable electrons, or 2 liable, no, 4 liable electrons, and that we just went through that, which that would be a fraction. N would be a fraction.
There is a bigger problem. You don't even have to worry about, you're wasting your time if you're counting electrons for that molecule. There is a bigger, much bigger problem.
Sigma wall.
Oh.
It's got a sigma wall. The electrons, the monkeys cannot cross that wall. So this is a major problem. The moment you see the sigma wall, you say, nope, it's not. Don't waste your time counting electrons.
Professor, I have a question.
Yeah.
Does that have alternating double bonds?
It doesn't have alternating double bonds.
Okay.
It only has alternating double bonds here and here, but in order for it to kind of spin around, it had to have an alternating double bond down here somehow plugged in. That's not possible because you only have 1 carbon. So that guy has a major problem. It's got a wall. The monkeys cannot jump the wall. Okay? It has to be an empty stick or a stick with a raccoon. That's the lone pair. Okay? Monkeys running with raccoon. Just, you might have a dream tonight. So this is a sigma wall, sigma bond, sigma bond, sigma bond, sigma bond. This is a sigma wall, so it's a no. Or you can say it doesn't have, as you said, Adamina, it doesn't have alternating double bonds, so it's no. You can use the word sigma wall. I don't think any book talks about sigma wall. It's my invention, but I think it makes sense. Okay, number 3, not aromatic. Number 4, what do you think? Look at the rules. Rule number 1, cyclic. Check. It's cyclic. Alternating double bonds? Not really. It doesn't have a double bond down here. But the good news is it doesn't have a sigma wall. Why doesn't it have a sigma wall? Well, it has a hole. It's got an empty pole. Okay? It's beginning to rhyme, and maybe someday we'll have a song from here, aromatic song. Okay, it's got an empty carbon, no electrons. It's got a hole. The advantage of having a hole is that the monkeys can still run around. Okay, even though there is no monkey. So then the bottom line is that means you need to move down to the next rule, the last rule. How many labile, L-A-B-I-L-E, labile, L-A, Los Angeles, bile, B-I-L-E, bile salt. Okay. How many labile electrons does this molecule have? 1, 2, 3, 4, nothing here, 0. Carbocation means nothing. It's got an empty p orbital. It's got nothing there, no lone pair, no extra electrons. So you count 0. 1, 2, 3, 4, and nothing, 4. Will 4 work? Will it fit the rule 4n plus 2? It won't. Are you guys following me? So the number of electrons is, labile electrons is 4, therefore bad news, no. Any questions? Quick questions. I think we're almost at the time level. We have 2 more minutes. This is no. Number 5. I want one of you to take charge.
I can't see what it is that you put on the bottom of that. What's in those circles?
Okay, it's got a lone pair. So it's a carbanion. Okay, let me just, hold on. Give me a second. So it's got a carbon. It's got a hydrogen. Can you see that? And it is a carbanion. It's a negatively charged carbon with kind of like a lone pair. It's not a lone pair because it's making the carbon negatively charged. If the lone pair was there and the carbon was neutral, then it's a lone pair. Like here, it's a lone pair because that's the number of electrons nitrogen is born with. Okay, so it's a carbanion. So double bond, and the lone pair. How do you count the labile electrons here? 1, 2, 3, 4, 5, and 6. This carbanion, unlike this guy and this guy, has 6 electrons. Therefore, what do you think? Is this aromatic or not aromatic?
Aromatic.
Aromatic.
This is aromatic. What about this molecule? When you have a non-carbon species, a nitrogen, okay, the nitrogen has 1, 2, 3, 4, 5 electrons around itself. I told you that sigma wall is a bad idea, but carbocation may be okay, carbanion may be okay, lone pair may be okay, as long as the total number of electrons can be written as 4n plus 2. Okay? So the number of electrons for this molecule, 1, 2, 3, 4, 5, and 6. Aromatic. Got it? we're going to stop here. There will be a quiz at the end. I'm not going to give you 40 minutes to do 5 questions. The time will be less. And it's going to be very similar to the previous one. Only difference will be that hopefully I won't screw up the key to one of the questions. So this is very important, what we discussed today and in the previous class. I'm going to take a snapshot, and while we are kind of hanging up, you can ask me any questions if you want. Don't write anything on the chat because I don't think I'm going to look at the chat. You can just unmute yourself and ask me any question if you have any. And I'll post the pictures and I'll post the recorded video whenever I get to it. If not, we're going to break today. Be safe, be healthy. Don't do anything funny. Don't go for a volleyball contest, as one of our son's friends asked him to come and play volleyball. He said, "Are you crazy?" So you should say the same thing if someone offers you, "Let's go for shopping in the mall." Don't do that. Study what's aromatic, what's not aromatic. It's not that difficult. If you have any questions, you can email me and I can answer you as well as I can. Okay.
So just to clarify, we're just dealing with these aromatic rules that we went over today on the quiz Wednesday.
Yeah. So yeah, since the last exam, this is our first class, right?
Yes.
Yeah. Pretty much aromatic stuff. I didn't ask any aromatic question in the previous exam, so anything aromatic is fair game. Okay.
Okay. Great.
All
Thank
right,
you.
guys. Have a good day. Rest of the day.
Thank you.
You
Bye.
too.
Bye. Take care.
Bye.
Bye.